Coding a password generator in C is probably very simple, I think. All we need to do is somehow get truly random bytes of data and then convert them to text somehow and then display that to the user. Of course, the user can state how many bytes of complexity the password should be. And the bigger the password, the safer it is, of course. So that's what we're going to do in this episode. We're going to code a simple password generator. And at the end of this episode, we will have a simple, small program that the user can invoke, passing as input a number of bytes and then getting as a response a password. And that's it. The main difficulty is just to get true randomness, but that is it's not really difficult. It's just something you have to consider. All right, let's start by going into the projects directory and creating a new directory, password generator. And let's cd into that. And let's create a new file. Let's call it parsgen to make it a bit shorter, and let's include standard IO for some basic communication with the user, and the program will accept one argument as input, so we have to pass that to the main method. So first argument is the argument count, which is 1 or 2. We will have to see, and then a string that is passed as an argument. That is the argv array. Yeah, so multiple strings that can be passed as arguments. All right, and we basically just printf to the console, generating password of, and then a number of bytes. Don't forget the new line at the end, and then we will pass in the number of bytes. So let's call it length. And that is an integer length, and the integer contains the number that was passed via argv and is the first entry, not the zeroth. The zeroth is the name of the binary that is being executed, as far as I know. And we have to convert that to a string. To an integer. I think that can be done using a to I from the string.h library, string.h. But let's look that up in a second. Man a to I. Yeah, convert a string to an integer. So this is the method prototype, the function prototype. We pass an input string and get as a result an integer. All right. And there are also similar methods that return a long or even a long, but those are not necessary. I mean, who wants to generate a password that has billions of characters? It's probably, is there a use case for that? I'm not sure. Except, of course, in password files. But here we are speaking about simple, basic passwords. All right, now we have obtained the length. And then I think we can already start executing it. Oh, wait, let's also check the number of arguments. So if the arg count is not 2, then the program should output printf usage and then parsgen and then a number of bytes. Okay, and then we can return here. Return -1 because let's return 0 because the program exited nominally. It just had wrong input arguments. Okay, and then over here in the pane below my webcam, we are going to compile the project. using GCC. And I get a warning. What is that warning? Implicit declaration of function a to I. Probably I have the wrong import. I imported string.h. Let's see where it's coming from. It's from standard lib. Yeah, I should have seen that earlier. Standard lib. And let's try to compile again. And it's compiled. And now let's execute it, still in the bottom right pane. And let's see parsegen. And we get a usage prompt if we don't specify the number of bytes. And if we execute parsegen with a number such as 60, then we get generating password of 60 bytes. So we are properly parsing the input, which is great. Now, all we need to do is we need to get a password of that length. And to do that, I would say we need a new method. It should return something. I would say let's first allocate some memory for the password. Should we allocate memory? I think we should allocate memory for the password. So let's malloc the length. It's as simple as that, I think. And then we get a pointer to some memory area. Password. It looks almost too simple. And then we'll then we'll create a method that returns nothing. It's just void generate password. And we will pass the memory area, memory, and we will pass the length. Maybe it should be a size t. Size t is better. As integer. No, I think int is okay for now. Otherwise, we have to cast this integer to size t. I don't want to do that right now. And don't forget to free the password as well. Otherwise, it will stick around in memory. And then then we call the method generate password with the password memory area and the length. And then we print the password, printf, and generated password. Then we print the password on a new line and supply the password again. And then I would say, yeah, that's fine. That's fine. Let's execute. And as you can see, nothing happens because I forgot to compile. So let's compile and then parsegen 60. And I get a warning that this right here is a void pointer, not a constant character pointer. And I should make that a constant character pointer. And also cast this to constant character pointer, although the keyword constant is not necessary here, I think, because it doesn't affect the size in memory. All right, now we should also change this memory area here, const character. Maybe it should not be constant because we're going to write into that memory. Wait, if a pointer is constant, does that mean we can't change the content of the pointer? The content of the memory area the pointer points to? Or does that mean we cannot change the address? I remember reading about that recently and forgot. But I think the difference is not too important in scope of this video, so let's just continue. With generating a password, and we can do that. Wait, I will just try to compile before we generate a password, because I want to get rid of the warnings, and then we will find out how to get all the random data to fill the password. So free password, passing argument 1 of free discards const qualifiers from pointer target type. Yeah, okay. So let's, I think that means we can't change the data that is written inside that memory area. Okay, so this works in principle. So here we are compiling the software, then calling it immediately with an argument of 60 bytes. And then the generated password is printed here. But right now we are not printing anything because we haven't generated the password. So technically we could now write something into that memory just to validate this. So let's do memcopy. And I want to look up the documentation for that. And there's, yeah, it's in string.h, memcopy. And here we can copy from a source to a destination of a size. So let's memcopy. The destination is the memory. The source is, let's just say this, and the size is 4. I would just want to mock something. Yeah, and as you can see here, the generated password is printed to the command line, and it's HHHH, and that means that it has been it has been stored in memory temporarily in the heap. Okay, but we don't need that, so I have removed that, and now let's check randomness. And if we do man random to get the man page for randomness, we get a couple of functions here, random, srandom, and those are pseudo-random functions, which are either just random void, I think, that just returns you random long int, but it will only be pseudo-random. So the first execution of that program, I think, will always return the same random value. Then there's srandom, which is basically a random number generator with a seed. So if you use the same seed as another person, your passwords will be the same. And yeah, those are all pseudo-random numbers because they are generated somehow on the system. We don't want that, we want true randomness. And if we look up the help for the man pages, you can see that we can use this what is flag to get some more insight into the man pages. So we can call man what is and then random. And here we see that there are 3 different types of random manuals. The first one is a manual of type 7, which is an overview of interfaces for obtaining randomness. Then random of type 4, kernel random number source devices. And then random 3, which is random number generator. As far as I know, the type 3 manuals are always for the standard libraries for C. And we're going to have a look at random 7 and 4 now. Because let's check the original man random, which we entered earlier. As you can see, this is the random 3 manual here. If we do man 7 random, we get some overview over the... Wait, let me just reformat that page so you can read it better. Now it's good. As you can see here, there are a couple of... Well, this is basically an overview. And this is about the kernel random number generator. And it relies on entropy gathered from device drivers and other sources of environmental noise. So this is apparently true noise. and it seeds a cryptographically secure pseudo-random number generator. And this is the keyword, cryptographically secure, so this should be good enough for our purposes. We're still using pseudo-random number generator because, of course, we're dealing with a computer, so nothing is truly random. It's all binary computation, which is always deterministic. But we are generating a cryptographically secure seed from true entropy gathered from the environment. So that's a good thing. And there are two devices called urandom and defrandom, and both are described in random 4, so in the other manual. These devices have been present on Linux since early times and are also available on many other systems. There's also the Linux-specific getRandom system call. This system call provides access either to the same source as def-urandom or to the same source as defrandom, so it's connected to one of those. Okay, that's interesting. So my plan for this video was to read data from those streams directly from def-urandom and defrandom. But there's apparently also this system call. Let's look that up, getRandom. Yeah, and that obtains a series of random bytes. And I think it writes those bytes into this buffer of a specific buffer length, and you can give it some flags. Yeah, and getRandom draws entropy from the urandom source, or as the other page said, from random. But this man page just states urandom as a source. That's cool. So now I would say, actually I wanted to make this video about reading stuff from streams, but now it makes way more sense to try to use this function. So I'm thinking, should we go and read from the streams ourselves or use this function? I think it's very nice that there's this function, but I think it's a bit more fun to read from the random number sources ourselves. So let's look them up. And I think there's a bit more to learn. So store somewhere in your brain, keep that thought, that there's this function getRandom, which really retrieves random numbers from def-urandom. But in scope of this video, we're going to access those random number source devices directly. So these are so-called character special files, and they provide an interface to the kernel's random number generator. So let's have a look what those files do. If I do tail f and then def random, nothing. I get nothing. And if I do def urandom, I get nothing either. Probably the issue is my tail f command. I would have expected that those... Wait, what if I do less to read those directly? Yeah, it's not a regular file. Use -f to see it. Let's -f. Yeah, and as you can see, this contains a bunch of random data. And I can't even quit. Yeah, I can quit. I can quit. And if I do def urandom here, then we see this data blob here. Let's go to def and see if we can what we can learn about those files. Right, let me just do lslh and then grep random. And there they are. And they have this one flag. I think this is a type. No idea. Okay. So let's learn about urandom again. wait, what happens if I do the following? I cat def urandom, and then I get the first line or the first couple of lines. Oh, then as you can see, we get a lot of random data. And if I invoke that again, I want to find out if we still get the same kind of data. Because somehow I have the feeling, because tailf didn't work, which is normally viewing the data live, the stream live, I would have expected this to print out stuff immediately on the console, and it would be, you would see a stream of inflowing or outflowing information. Let's see what happens. Let's remember this string 9D, and it ends with CPT. Yeah, and if we invoke it again, we get completely new random bytes. If we invoke it again, new random bytes again, and if we invoke it again, we get new random bytes again. Okay, perfect. I think that's enough. The difference between def random and def urandom is, by the way, in their blocking nature, if I remember correctly. Yeah, as you can see, the def random device is a legacy interface which dates back to a time where cryptographic primitives used in the implementation of def urandom were not widely trusted. It will return random bytes only within the estimated number of bits of fresh noise in the entropy pool, blocking if necessary. So this waits for entropy to be gathered and then blocks. Def random is suitable for applications that need high quality randomness and can afford intermediate delays. Oh, so maybe actually we want high quality randomness. But yeah, so def urandom is probably secure enough. It's faster. And def random is super random. It's just super random. And therefore it's a bit slower. So you can decide between super random and regular random. All right. How do we read from those files? We can use the function fgetc, which takes as input a file descriptor. And I know that because we have covered this function in the last episode, where we implemented a printf clone using those couple of functions here, fgetc, fputc, and those related functions. And fgetc takes as input a stream and returns an integer. And this is an integer read from that stream. So what we can do is we can just specify that we want to use the random stream. Now, wait. One interesting point is that for other streams, such as standard out, there exists a file pointer that we can already reference and see. I don't think that's the case for the random file streams. Yeah, maybe not. So we have to open the file ourselves. Maybe I'm wrong here, but that's my best guess for now. Wait, let me just disable my linter. It's annoying. Disable. And let's enable line numbers. Oh no, we don't need line numbers. Who needs line numbers? Only noobs. I'm just joking, by the way. Generate password. Okay. By the way, recently someone complained in the comments that I always take so much time to get the first relevant function call, and it's the same thing again in this episode. But I really want to understand the things that I'm doing here, and I really want to dive a bit into the topic before I just type out stuff. And I think that's what makes programming in your free time worth it. I'm not at work right now, and you're not at work right now. Maybe. And and the fun in programming only really flowers up and grows if you take time to read up stuff, because fun part about programming is the curiosity, in my opinion. So being curious about how different things work, how things interact, and finding out new stuff, learning things, having ideas. And if you just try to hack a solution quickly together, then it's not fun. Anyways, okay. I remember we have to use fopen, and then we can open a file. Yeah, and we specify a path name here and a mode. The path name is going to be, let me just fix that path name. Const character pointer, random file, or random stream. And that is equal to def random. We're going to use the super random one and see if it performs well enough. If not, we will switch back to urandom. And then we're going to pass as input the random stream here. And the mode is I think R for read-only access. Yeah, as you can see here, we open the text file for reading. The stream is positioned at the beginning of the file. We can technically append data to that stream. I don't know what happens. What happens if you append data to the random device? Write it in the comments if you know. So fgetc. So okay, we have opened the file now, and this returns such a file descriptor or file pointer here. That is called, let's call it just file. And then we get a character from the file. And that is an integer. Let's call it C for character. And we can even do some error checking if the character C is equal to, I think, end of file. Wait, what was it? fgetc. Here. No, null. So if it's null, then it's an error and the file could not be read. So in this case, we are printing out printf the file could not be read, and then we're supplying the file name random stream, just like this. And let me complete that string like so. And wait, what if I want to exit the program properly? The exit function causes normal process termination and the value of status blah 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 is returned to the parent. I think I can call exit here instead of just return, and that will properly terminate the application. I hope. Let's just try with a -1 as an error code. Or do we get any error codes here? There are probably sample error codes. I just don't know them. I mean, predefined constants. Okay, so we have read from the file. If we reach this line of code, and now we actually have to pass. We have to paste the character into our password. However, wait. This just feels unnecessarily complex here. We get individual characters and then put them into the memory. There's probably a way better function to copy a file. Maybe let's look up copy. Man. What is copy? Is there something copy? No. Memcopy. Who cares? Let's just do it the hard way. So we are going to read characters while C is... No, we can use a for loop because we know the length. So I is smaller than length, and then we increment I. So yeah, let's keep things simple, simplistic, beginner friendly. And now we can, inside that loop, we can put all of that stuff inside that loop. I don't know if we should really null check every single character here. It's probably only really less necessary for the first character, so let's maybe not put it inside the loop. So this is just a dummy check if we can read the file, and if we enter the for loop, then I can just assume that we can read the file. So let's write into the memory area, dereferenced, the character C, and we need to access the memory area dereferenced memory area plus I to loop over the individual positions in the memory. And here we write a random character, and we can just do a fgetc file and then assume that it will return some random data here. That's nice. Okay. Is that it? Let's try. So looking at the terminal below my webcam, let's see. Okay, we have a generated password, but it has messed up the terminal. There's even a Chinese character inside, which indicates that it's really random. I don't know what this is. One in comparison between pointer and integer. Okay, but didn't we just look up the documentation that fgetc can return null? Did I misunderstand that? Fgetc, let me look. No. fgetS returns S on success and null on error. fgetc returns end of file on error. Yeah, that's why I had this intuition that we have to write end of file here. Alrighty. And then let's try again. Okay, this is... Oh God. Yeah, we are generating a random password of 60 bytes. Yeah, fine. But it can contain invisible characters and line breaks and whatnot. Tabs, probably everything. It can contain everything. So maybe visualizing it like so, including those Korean characters, is not the cleverest choice. Maybe it makes more sense to print it to the console in a different way. Maybe it should be a hexadecimal. No, not hexadecimal. That's probably too long. But maybe it should be... Wait, how can we properly print it to the console? We have truly random integers here, or truly random characters that we retrieve. We are writing those truly random characters into the memory, and I want to visualize it using Unicode or ASCII, maybe ASCII. ASCII characters are safer because Unicode can be probably anything from any language, which we don't want because not all websites support Chinese, Korean, or Japanese, or Arabic, or whatnot characters. So we have to keep it simple. So let's look up C print, byte to ASCII string. We can manually convert it, maybe. Characters and integers are stored in binary in C and can generally be used in place of each other when working in the ASCII range. fprintf, that should print A to the screen. Yeah. What happens if we... Let's go into the debugger. Let's go into the debugger and see what the memory actually contains. So to do that, let's compile the program with the -g flag, and I will also use the -w all flag to just be sure that there are no warnings. And then we can call GDB with passgen. Wait. Yeah, I will create a new window for that. So let's see into projects, password generator, and then GDB, passgen, layout. Next, let's go to the source and let's put a breakpoint in line 34. And let's run. And we have an exit. Because we have to set the arguments, of course. As you can see here, we are running the program and we get, we haven't supplied any arguments, and that's why it terminated. To do that, we have to set args, and let's generate a 32 bytes password, and let's run. And now we are here in line 34. Let's refresh to fix up the screen. And now we can print password. And as you can see, we have, I think, 32 bytes of data. That's the pointer value, then the address in the address. And that's the value that the address is pointing to. So we have filled random data. I just don't know how to properly make it an ASCII character, because there are not so many ASCII characters. C byte to character. Okay, let's look up man for ASCII. It probably exists. Oh yes, it does. That's awesome. I always used to look up those things on Google. ASCII is the American Standard Code for Information Interchange. It is a 7-bit code. Many 8-bit codes contain ASCII as their lower half. Okay, it's just 7 bits. So if we use ASCII and we reduce our characters to ASCII, does that reduce the security of our password? I mean, actually, I really want to, if I specify a password of, let's say 60 bytes, that it's really 60 bytes of complexity. And this one seems to be, yeah, and actually this is the correct solution, what we're seeing right here. This is truly random 60 bytes of password data. And this as well. The issue is just that this is not really usable on many websites, on many internet services. So it might make more sense to compress or somehow limit the number range onto ASCII. And this probably means that we are losing some precision and some complexity, but it might be the best thing to do. Okay, we can start at at index, yeah, those are decimal indexes here, indices. At index 32, there's the space character, and then following those, following that are the special characters, numbers, more characters, up to which index? Up to 126 only. Okay, how do I mean, it's not a problem to compress the random values that we have and convert them to those ASCII characters. The problem is rather, how do we keep up the 60 bytes complexity? Is it still 60 bytes if we just shift the representation of those bytes? Yeah, no, it's I think we have to use a bigger character set. Let's look up some character sets. Man character set. Nothing, no entry. Character set like this, maybe? Oh. Okay. Then character sets. Which character set for passwords? A mix of uppercase and lowercase letters, numbers, and symbols. Yeah, super. Unicode. UTF-8. Wait, what's the difference between UTF-8 and ASCII? Maybe that is what we need. Wait, man UTF-8. I just need a character set that has 255 characters, at least 255. Okay, that seems to have a 16-bit code space, which is even too much, but why is it called UTF-8 then? Okay, there's lots of technical detail in here. Okay, programmers are accustomed to single byte encoding such as US ASCII or ISO 8859. Have to be aware that two assumptions made so far are no longer valid in UTF locales. Firstly, a single byte does not necessarily correspond anymore to a single character. Yeah, but this is a good pointer, actually. What if we look up this character set? ISO 88, man, ISO 8859, nothing, 8859, nothing. But this character set says... Oh no, forget about it. The issue is always that if we accept truly random data, then some of the characters generated will be new lines, end of files, and those things which we don't really want in the result. But this one looks a bit complex, honestly. One byte character encoding. Unicode uses 2 bytes to represent all characters in all writing systems in the world in a single set. That's Great. And UTF-8 uses 1 to 4 bytes per character. ASCII seems way more friendly. Yeah. I'll use ASCII for this project. So we have to do the following. We are wait 1 second. We are generating, or we are getting a character from the random number generator. Now we can fill that here. Wait, int. Let's call it R for a random character, and R is equal to fgetc from the file. And now we have to limit R to the range 32 to what else? 126. 126. To do that, we can use modulo, I would say. So R is equal to R modulo 126. No, we can't do that because we wanted to start at 32. So R is equal to R plus 32 maybe. Oh god. It's so easy, but why am I failing at this? R modulo 126. This gives us the range 0 to 126. And then we should modulo that. No, then we should increase that by 32, which gives us the range 32 to 126 plus 32. And then modulo that again. Oh, that's horrible. This feels so wrong, but I'll trust it. So let's, oh, wait. As you can see, we are generating a password that looks reasonable. What is that character? Where does that come from? That doesn't look ASCII at all. Okay, let's try to generate a password of 1 byte. It does not give us an output. So something is wrong. If we do 2 bytes, we get a character, a single character, or 2 characters. Something is a bit off. So I don't like that. What? Let me just printf the value of r. I know we can debug this, but let's just do it. Oh no, okay, let's do it properly. Let's debug it. Let's quit out of here and then gdb passgen and then layout next. And where's the source? Oh, did I compile without source? Without the debug symbols? No, wait. Oh yes, I did. So I have to append -g -w all as well here. Now we can do it. Layout next. And then we'll put a breakpoint at line 22. Then we'll watch the variable r. R doesn't exist yet, so we have to run. Refresh set argument to, let's say, 16 bytes. Let's run and let's watch the variable r. Let's hit next. Wait. Refresh. So we are in this line. What happens if I do next? Old value is 1, new value is 16. Let's hit next. Old value is 190, new value is 0. Old value is 0, new value is 96. Wait. How can I remove the breakpoint? Wait, I have to... I think I can clear it. Clear 22. Yeah, let's put a breakpoint here in line 23 and let's run. No, don't run. Continue maybe? Okay, let's print r is 25. That's already wrong. Continue. Print r 47. That's okay. Print r is still 47, of course. Print r 85. Continue. Print r. Of course. I'm stupid. Watch r, continue. Continue. Now it has value 0. Why? Now it has value. Maybe my watch point was wrong. Yeah. Okay. Can I just do if r is bigger than 126 or r is smaller than 32? printf alert. I can probably do that in the debugger as well, but let's do it like that. And it's alerting me. That means something is wrong with this statement. So R modulo 126 results in numbers between 0 and 126. Then plus 32 results in values between 32 and 158. Modulo 126 results in values that are between 0 and 126 again, I think. We have to modulo it by 126 minus 32 and then add 32 on top. I think this would work. Yeah, let's try. And let's generate a password of 60 characters. No problem so far, no alerts. Yeah, I think this time this works. Okay, perfect. Now, if we clear that and call the password generator 60 characters, we get a couple of spaces. Are they true spaces? Maybe let's remove the spaces just to be sure that that the empty characters are not invisible or invalid or whatever, those kinds of characters here. So let's start the range at 33. And we can do that by, of course, replacing 32 with 33. Okay. And here, wait, did I still have an empty line or a new line character in there? That looks okay. That looks okay. That looks okay. There's a line break or empty characters. What's that? That's all so weird. 126 minus 33. Write that stuff into memory. Maybe the I don't have a good reason what's going on occasionally. Here you can see the password is like just those couple of characters and there's nothing behind that. And why is it using this character, not something from the ASCII data set? I think that has to do with my terminal. I don't have a better explanation, honestly. That's weird. Why are there non-ASCII characters in between? One thing that we could do is actually print those R's. Wait. Ah, no, I'm stupid. I'm so stupid. Please, guys, please. If you saw this before me, I'm so sorry. Bookmark this moment. This is a moment in programming history. The world's biggest or most stupid bug ever. I'm getting a character here in this line, and then I'm not using it, and I'm creating a new variable, a new random character here that is not polished. So obviously I have to write the polished character R into the memory, and that should be it. Here's our random password that is completely part of the ASCII data set. Yes, as you can see, now it's working. So those are maybe not 60 bytes now because we're printing ASCII characters, but let's change it to number of characters. Number of characters. And yeah. So this was the stupidest bug ever. The stupidest bug the world has ever seen. That's crazy. So guys, everybody, here we have our generate password method that generates a password by opening the def random file stream, and then it's writing those random numbers into memory. It's just limiting the range of the characters to ASCII. Therefore, it's not as complex as we could have it. It's not just random bytes, but it's random ASCII characters. But still, it's very, very powerful because now we can just do, or maybe let me just create a new view here. This is not looking good. Let's do this. Let's scroll this up to the password generator function. And down here, we can now generate our passwords. Let's cd into the password generator. And here we can call the parsgen. And let's say you want a password that is for everyday use, maybe 24 characters. And there you have it. Then you can actually also, check, is my password secure online? Maybe we can also program such a thing ourselves. And let's go to this page, how secure is my password.net, and then we can enter that password. This tool is now, yeah. Hey, let me copy that. And okay, this thing was spamming me. Let's try it here. How secure is my password? And let's try the generated password. Let's type a password. It's very strong. It would take 1 billion trillion years to crack. Yeah. I'm not sure if it's really that strong. Yeah, it is strong. It's strong. Yeah. If you have ever done any brute forcing, you can tell it's strong. But what about just 6 characters? This would be this short password here. Let's check the password strength of that one. That should be not as strong, but it's still considered strong and still would take 24 days. I'm not sure about that. No, I could crack that faster, I think. It's just 6 ASCII characters. I don't know, but okay, anyways. This episode was super much fun. I really enjoyed this, diving into the random file streams, into random numbers on Linux, into fgetc and putting things into memory and limiting things to the range of a character set. And all of this is super nice and it's a lot of fun. And now we can just generate passwords of an arbitrary length, such as 10. And there's our password here. Or we can do 15 15, just like this. Or we can even do 150. It doesn't matter. We can generate really generate passwords of arbitrary size, 600. There we go. So we can really generate some super secure passwords. I hope you also enjoyed it. If you did, stick around, leave a like, and see you next time. Bye.